Welcome back, class. Today we're going to start a new unit on numerical integration and differentiation. Today we're going to start out talking about numerical integration. Here we're going to use computational approaches to solve integrals from either tabulated data points or data points that we can calculate. Just as a reminder, we closed out our previous section on line fitting by talking about splines and piecewise interpolation. Hopefully you feel confident with using fitting lines to several different subpieces and using that to fill out, to model a whole line. We're going to use this in calculating different integrals. Today, what I want to talk about is the Newton-Cotes approach to integration. We're going to specifically tackle three different subsets of Newton-Cotes, particularly the trapezoidal rule, Simpson's 1/3 rule, and Simpson's 3/8 rule. Then we'll talk about how we can apply these in a composite type formula. But here we're only going to talk about the trapezoidal rule and the 3/8 rule. Finally, we'll talk about unequally spaced data. I'll touch very briefly on open and closed methods, and then we'll talk about multivariable integration. So just as a reminder, an integral is the area under a curve. So let's say I have this f of x and this x. If I want to take the integral of that function from a to b, what I'm really asking is how much area is under that curve. Or in other words, if I can sum up the value points at each of these of f of x at each of these points all the way through here, right? So the main way that we're going to numerically approach integration is through the Newton-Cotes formula. The idea with this approach is saying that this integral, this definite integral from a to b over some function f of x can be approximated by an integral over some interpolated polynomial f of x, which is easy to interpolate. So let's say this is hard to integrate, and this f of n is easy to interpolate. We can approximate the hard to interpolate formula by the easy to interpolate formula. So let's look at a few examples. We can do this in several different orders. So we could take, for example, this point here and apply just a straight line, just like we were fitting data using in our interpolation schemes, right? So I could fit just a straight line from a to b, and then it's quite straightforward how to take the integral under that straight line. We could do a higher order polynomial, say a parabola using 3 points on this function. And then once again, we could interpolate, find the coefficients for that parabola, and then integrate over that area. We can do this in either a single step as shown up here, where I'm going directly from a to b, or we can do this in a series of steps, or a piecewise approximation, where I take several steps along this, along the function, and I can do that with several different orders of interest. So let's get into it. We're first going to take this first order approximation where we're going to just take straight lines. This is going to be called our trapezoidal rule. Here we're going to use a straight line approximation. So what we're going to do is change this complex function for a trapezoid. What we can do is we're going to, if we know the point at A and the point at B, we're going to fit a straight line. Hopefully now we've become relatively good at fitting a straight line, and we can say that this straight line has a function f of A plus the slope f of B minus f of A all over B minus A times x minus a. right? Just from, hopefully you're remembering that from our line fitting segment. I can take this entire formula, put it into this integral, which should now be relatively straightforward, right? Because we know what f of a is, we know, and we know how to take the integral of this line. When I do this out, we end up with this formula. We have the integral is b minus a times the quantity f of a plus f of b over 2. This is the same integral. This is the same formula as the formula for a trapezoid. So the a of a trapezoid is that width times height 1 plus height 2 over 2. We can see that this matches exactly where this x is this distance, and these heights correspond to our a and b. So this is why we're called, it's called the trapezoidal rule. Next, I want to talk about the error that's associated with this. We can estimate the truncation error using this formula here, where we can say for sure that the true error is -1/12 the second derivative of our function at some point along the a to b range times b minus a cubed. So let's say I'm taking this integral from here to here over this entire section. The error is everything that sits above that. So in this upper shaded region. My true error has to be -1/12 the double prime over that epsilon. The question is, we don't know what that epsilon is. But what we do know is it's going to depend on that second derivative, or in other words, the curvature of that function. And we also can say by this formula that it has to deal with the distance between a and b cubed. So there's that a cubic relationship between the width and the error. What this is telling us is if b minus a is very big, I'm going to get a large error. Similarly, if the function is highly curving, so that second derivative is large, I'm also going to have a large error. We can't really change the curvature of the function. The function just is what it is. What we can control is this width over the curve. So what we can do is try to break this up into small pieces. So the more small pieces that I break it up, say over here, the more accurate my error should be. Let's take a look at an example. First, we'll do it in a one-shot space, and then we'll try this error-reducing method of breaking it up into small pieces. So let's numerically integrate this fifth-order polynomial shown here. And we're going to do it from a equals 0 to b equals 0.8. And then we're going to determine the error and an estimated error. So let's write out our equation for our integral. It's b minus a, so that's 0.8 minus 0, times f of a plus f of b over 2. To get these f of a and f of b, all I need to do is plug 0 into this top equation. When I do that, I'm going to find that f of a equals 0.2 and f of b is equal to 0.232. I can then plug in our equation. We went over a little bit, but here we go. We can then plug those values into our integral, or our trapezoidal rule formula, and we find that the integral is 0.1728. This is great. So now we have an estimation for our integral. Now, I'm not going to do out the math, but we can do this integral exactly. And this because we can take the integral of this polynomial dx and plug in our a equals 0 and b equals 0.8. If I do this, I end up getting 1.64053. I can now get the true estimate for that error. Maybe I'll put this over here, I exact. So this gives me a true error of 1.46. This isn't the percent error, just the actual true error. So what we can see is we're relatively far off. I can put this in terms of a percent by dividing by that 1.64. When I do that, I find that I have a 90% error in my a 90% error in my estimate for this integral. Now let's look at an estimate of the error. What we're going to need is to take a second derivative because it shows up in our formula right here. So I can take a second derivative of the formula for that polynomial, and I've written that out here. The question becomes, what is the what epsilon value should I use? Well, instead of taking any one value, what we could say is let's take the average value of that second derivative. So my average value of the second derivative should be my integral of that function over from 0 to 0.8 over the range of x's, so 0.8 minus 0. I can do this analytically, and it would come out to be negative 60. So therefore, my approximate error can be written out as negative 1/12 times 60, which is my approximation for my second derivative, times my range over which I'm looking, so 0.8 cubed. And this gives me 2.56. You'll notice that this is significantly larger than my true error, which was 1.46773. So this approximate error is going to give us that an upper bounds of where we should sit. However, we're still relatively high, right? We don't want to have our error being this large, especially if I'm looking at, say, a gas chromatography column and trying to figure out how much, say, of a substance has come through that column, right? I want a much better error than over 100% or roughly 100% error. We said that we could do this using by splitting the data up into several pieces. So this is shown over here, right? So I could split this up, instead of going from 0 to 0.8, I could split this up into several sub-pieces. Let's do that, and let's assume that we're going to take n+1 data points which are evenly spaced, right? So instead of having, you know, a point here, and then a point way out here, and then several small points here, let's make this evenly spaced. By evenly spaced, I'm going to treat that data more evenly. Therefore, I can rewrite my equation, my integral equation, from being I equals the integral from x0 to xn, or my function fn of x dx. And I can split this up into each data piece. So I can go from x equals 0 to x1, x1 to 2, xn minus 1 to xn. I can split this up into a whole bunch of pieces and then apply the trapezoid rule again and again and again. If I plug in my equation, I can get this formula. So my integral is x1 minus x0 times f of x0 plus f of x1 over 2 plus x2 minus x1 f of x1 plus f of x2 over 2. And I can do this again and again until I get to the end where I can say xn minus 1 times f of n minus 1 plus f of n over 2. So all I've done is I've taken that equation for the trapezoid and I've plugged them in to these equations repeatedly an n number of times. Okay, so if we said that our data was evenly spaced, we can make an assumption for what x1 minus x0 is. We can say that this is going to be h, right? This is our I plus 1 minus xi. Right? So this is how many spaces that we're going to set it up. I can then pull coefficients out, because if each of these data points are evenly spaced, I can pull them out and I get this h over 2. And then I have the rest of my terms. It ends up being that I have f of x0 plus twice the sum of f of xi plus f of xn. Okay, so as I'm moving on, I count all of my points. I get to count all of my points. And then I will note that this piece, this x, f of xn, lies outside of that summation. So maybe I'll put some parentheses in here just to clarify. Where this is coming from is because when I take this trapezoid, this second point is counted in the first trapezoid and the second trapezoid. So that's why we have this 2 out front. Whereas the x0th point and the xnth point are only counted once. So they don't get that 2 in there. Let's go back and use the exact same equation that we did before, but let's use a composite trapezoidal rule. Let's do this in 2 segments. So the first thing that we need to look at is what is our h. So if I have n equal to 2, that means that I'm going to take my h is equal to a minus b over 2, right? Because I have 2 segments. So this is, this should be b minus a over 2. So this means that I should have 0.8 minus 0 over 2 is 0.4. This gives me my h. I now need to go in and calculate my formula values at these different points. So we need at 0, we need our halfway point. So x1, which should be at 0.4, and x8. Here I'm just pulling those values, just writing out those values by plugging in these different x's. So x1, x0 equals 0, x1 equals x0 plus h equals 0.4, and x2 equals x1 plus h equals 0.8. Right? So I can plug those in. Now I can go in and I have the h that I need. I have f0. I've got all my internal f's, and I have my fx. Now I'm ready to go in and plug into my equation. So we can say that I is equal to h, so 0.4 over 2, times the quantity f of x0, so 0.2, plus 2 times the sum of all the middle points, so that's 2.456. I only have one middle point, so I don't have to worry about anything else, plus my end point, my f of xn, which is 0.232, and I'm good to go. If I do this all out, I didn't give myself much space, but this equals 1.0688. I can now go in and calculate my true error. Once again, taking the true value of 1.64, subtracting off my approximate error using the composite trapezoidal rule, 1.0688, and that gives me 0.75. This is telling us that we have only a 34.9% error. I can calculate my approximate error by using that equation, negative 1 over 12 times the second derivative times b minus a cubed. So here's I'm still retaining that 0.8 cubed for b minus a. I have my negative 12 over 2, and then I have my 60 approximation. This is going to give me 0.64. Here I have this 2 squared because I need to take that h into account. Right? So we can see that we're dropping in error as we're going through here. We can keep doing this point after point, calculating with smaller and smaller sized h's. So I can use n equals 3, n equals 4, 5, 6, etc. And we can calculate the appropriate h's going down. So by the time we get to 10 segments, I have h of 0.08. I can calculate my integral going out, and we see that we start to converge. So by the time we get to 10 points, we have a true error of only 1.6%. We're getting quite close to the exact value of 1.64. However, you'll notice that it requires us to calculate quite a lot of points. In this case, where we're only dealing with a fifth order polynomial, it may not be so complicated to calculate 5 points. But if we had a very complex formula or something that took a long time to run to calculate each point, it may be difficult to calculate each n. Or conversely, let's say instead of having a formula that we were going through and trying to calculate, we had data points that were evenly spaced. So we had some information that was coming out of a piece of analytical equipment. We can't necessarily just go in and say, oh, find another data point. We're stuck with the number of data points that we have. So we need to find a better approximation. Just like before, when we were doing line fittings, we said, let's not use a straight line anymore. Let's use 3 points and fit a polynomial. This is the idea behind Simpson's rule. Here, we're going to move, instead of taking a straight line, we're going to now start fitting higher order polynomials. So we could use 3 points along a line to fit a parabola, or we could use 4 points along a line to fit a cubic polynomial. And you can see that as I increase the degree of my polynomial, my fit, so my area under the curve, starts getting much better, and I can start doing that. Similarly, the error associated with my function is going to depend on higher and higher order second derivatives, so that the effect of those higher order second derivatives starts becoming smaller and smaller, and I get a more exact answer. Let's take a look at the first rule. So Simpson's 1/3 rule. This is going to come by fitting a second order polynomial. Here we're going to fit this polynomial across these 3 points using a Lagrangian polynomial. If you remember from our line fitting, this is the equation for a quadratic Lagrangian polynomial. Here we have our x terms out front, over specifically 3 points. I end up getting this I equals h over 3 times f of x0 plus 4 f of x1 plus f of x2. In this case, h is, of course, b minus a. So here's B and here's point A, over n. In this case, n is just 1 because we're only integrating over 3 points. I'll make one last note about this. What you'll see in relationship to the formula is we have extra weight being placed on that central point. If I had done this as two trapezoids, 1, 2, I would have ended up with the same set of points in this middle part, except I would have had 2 fx1 plus fx2. So this would be for composite trapezoid. And I have this h over 3 term instead of an h over 2 term. This 3 here, or this 1 over 3 term, is the reason why it's called Simpson's 1/3 rule, because we have a 1/3 h out front. Just as before, we can get an estimation for the truncation error of a single application of our Simpson's 1/3 rule. This is given by this equation. Here, we have the true error should be 1 over 2,880 times the fourth derivative of some point along that line times the approximation times the length to the 5th power. So we can see immediately that our error has gone down significantly due to 3 factors. 1, a much smaller prefactor. 2, the fourth derivative is likely to be much smaller than the first, second, third, etc. And lastly, we have the difference, the range of which we're looking to the 5th power. So as we're moving to smaller and smaller sizes, this truncation error should decrease much faster than when I had it only to the 3rd power. So we get a much faster convergence. However, just as before, we can say that we can decrease the error and increase the accuracy by breaking this into smaller parts. So you can see that by decreasing, by cutting the length in half, we have a decrease in error of 2 to the 5th power. We're going to put this into an example using the same exact equation that we had before, this 5th order polynomial from a equals 0 to b. And we're going to determine the error and we're going to estimate the error. So here I've written out the equation for Simpson's 1/3 rule. So this is h over 3 times f of x plus f of x0 plus 4 f of x1 plus f of x2. Here we're only going to do a single, here we're going to do only a single case. So we have, once again, we need to figure out the 3 points that we're going to work with. So here we have A and B. So B is given as 0.8, A is 0. We still have an H that's B minus A over 2. This is because I need to find out what that middle point is, right? So I'm going from between each of these points here. So this is going to be our H. So I can take my 0, 0.04, 0.8, and I can plug them into this top equation. So here I get 0.8 all over 0.2 plus 4 times that middle value, 2.456 plus 0.32. You may be asking yourself, where's this 6 coming from? Well, remember, H equals B minus A over 2, and then we take H over 3. So if I just look at that bottom piece, this gives us 1 over 2 times 1 over 3, which is equal to 1 over 6. Okay. So we can now look at what the true error of our system is. So this is the true value of the integral 1.64 minus my estimated value of the integral 1.367. And this gives me an error of 2.73. Notice how we've come down significantly from the error is in our trapezoidal rule, which was more like 50%. So now we're down to 16. Once again, we can look at what the approximate error is by filling in that equation. I'm sorry, by entering the values from this equation. Here we can take our b minus a to the 5th power here, and we can actually calculate what that average 4th derivative is over the range. It happens to be negative 2040. And here we can also see that my estimated error is going down as well. Just as with the trapezoidal rule, we can do a composite 1/3 rule, where we increase, we have several different parabolas set up. In this case, I take 3 points. So 1, 2, 3, and I take the integral under those 3 points. Now I don't want to, when I go to take the next spot, I want to start out with the integral under the next 3 points. So here's one interval, so interval 1. Here's one interval, interval 2. I can't go, over this next interval because then I would double count this piece. So I have to stack those integrals next to each other. So when I write out my equation for dividing this integral from 0 to n, I take the integral from 0 to x0 to x2 of fn plus the integral from x2 to x4 over fn, etc., etc. I can then use the Simpson's 1/3 rule equation to write out each of those pieces. So we get f of x, then 4 f of x1 plus f of x2. Then I still have my 1/3 piece out front, f of x2 plus 4 f of x3 plus f of x4. And then this pattern will repeat all the way until I get h over 3 times f of x n minus 2 plus 4 f of x n minus 1 plus f of x n. What you'll notice is I end up with these terms here. Let me pull these out here and here that are going to match. So these points are repeated because when I'm sitting at the interface between two sections, that point at that interface is used in both the calculation of the integral for both sets. So I end up with, in this case, 2 f of x2. So when I write this integral in a condensed form, I can pull out all the pieces that are only in there once. So this is my f of x0 and my f of xn, right? The two pieces at the end are only in there once. All of the odd numbered, odd indices versions have a 4 up front, right? If I'm looking, these odd pieces are always in the middle and they have a 4 up front. If I'm at an even internal piece, right, that's these cases where the data is on the edge of one interval and the edge of the next. So they get put in here twice. So when you're reading this formula, you have to keep track of your indices because the odd ones get multiplied by 4 and the even ones get multiplied by 2. Let's put this into practice with an example. Once again, we're going to look at our 5th order integral, and now we're going to do this with the composite 1/3 rule. So first things first, we need to pull this equation forward. This is going to tell us that I need my f of x0, my f of xn, I need an h, and then I need these internal points. In this case, my h is going to be 0.4 minus 0 over 4, sorry, 0.8 over 0 minus 4, giving me 0.2. So when I go to do out this equation, I have my x0, which is 0, my x1, which is 0.2, my x2, which is 0.4, x3, which is 0.6, and x4, which is 0.8. Notice how when I have 4 segments, 1, 2, 3, 4, it requires 5 data points. It requires an odd number of data points. I need that odd number of data points in order to fully fit my all of my different segments. Okay, so I've now come in. I can come in and I can take those x's that we had talked about before and plug them into my formula. When I do that, I can find that f of x0 is 0.2, of 0.4 is 2.456, etc., etc. It then becomes a matter of just plugging in these data points. So here, once again, we have the whole range over which I'm working. This 12 is coming from the 3 from Simpson's rule times my number of data points of 4. And then I can go ahead and plug in the pieces up here. My f of x0 is 0.2. I now have an odd data point. Remember, this 0.2 is x1. So I have 4 times 1.28. Plus this f of 0.6 is x3, so I have this 3.464 here. I now move on to my even points, so shown here on the left-hand column, so x0, x2, x4, and we can pull out these pieces. So I get a 2 out front because it's even, then I pull out my first even data point, so that's 2.456. I don't have any more even data points. The next even data point would be my fxn, so I don't have any more data points in there. But I do put that x equals 0.8, excuse me, out at the end. I can then do all of the arithmetic, and I'll find that my I equals 1.623467. If I compare this to my true error, let me move some stuff out of the way, which is 1.64, we can see that I'm getting very close to my true error. In this case, I'm only 1% off. So we can see that by moving from trapezoid to Simpson's 1/3 rule, we improve the error, and then as I move to a composite 1/3 rule, I improve the error even farther. As before, I can now calculate my error estimation, and we find that it's getting quite low, and in fact, the same as before. If I want to improve my estimation further, I can go to the next higher order polynomial, where instead of using a quadratic equation, I can use a cube. In this case, it's called Simpson's 3/8 rule. As before, the Simpson's 3/8 rule comes from the fact that we end up with this 3h over 8 out front. I'm not going to go through the ideas behind deriving this, but in essence, we end up taking 1, 2, 3, 4 points and fitting a cube from that. And then from that equation, we can get this, from the Lagrangian, we can get this equation. What you'll notice though is now all of a sudden I need 4 points. This is a lot of points to need, and I may not always have a number of points which is nicely divisible by 4. Therefore, I often have Simpson's 3/8 rule, where I'll take one set of 4 points, shown here, to do Simpson's, or maybe let me put this, I guess, the other way. I'll take one set of points, 3 points, and do Simpson's 1/3 rule on it. Then I can take 4 points, 1, 2, 3, 4, to do Simpson's 3/8 rule on it. So then I get a much better estimate out here, and then I can have a reasonable number of points by sort of filling in the ends with Simpson's 1/3 rule. Let's put this into practice. Once again, we're going to take the integral of this 5th order polynomial. I'm using Simpson's 3/8 rule. First, we'll do it Simpson's 3/8 rule, and then we'll do the compound formula. So for Simpson's 3/8 rule, we need 4 points. If I take 0.8 minus 0 over 4 to have my over 3 to have my 3 even segments, we get 0.2667. This means that my x0 is still 0, my x1 is 0.2667, my x2 is 0.5333, and my x3 is 0.8. We then can go in, solve for this function value at each of these different points, and the values are shown here as appropriate. I then can go in and use the Simpson's 3/8 rule out here. We have the a minus b minus a out front. This 1/8 comes from the fact that I have 3 times 8 times this 1/3 where I divided in order to find out how big my section pieces are. This leaves me 8 here. I then can go in and use Simpson's 3/8 rule, which says take f of x0 out front plus 3 times the interior points. So if I look at my interior points, they're right here. So 1.432 plus 3.487 plus my last term is just that last point. I can plug all these numbers in and I get 1.5197. So we're sort of starting to converge to this case, to our correct answer. Let's do this again using Simpson's 1/3 rule and Simpson's 3/8 rule for 5 segment pieces. Here I've broken this up into 5 pieces where our h value is equal to 1.6. This is coming, of course, from 0.8 minus 0 over 5. All right, so here I've already calculated the appropriate numbers for our x's, and I've put the numbers into this table. What we're going to do is we need to identify which pieces we're going to use for Simpson's 1/3 rule. So we're going to do this with the first 3 numbers. So on x0, x1, x2, we're going to use for Simpson's 1/3 rule, and then we're going to use these 4 points, so x2, x3, x4, and x5, in order for Simpson's 3/8 rule. What you'll notice is x2 right, is doubled because it forms the end of the first segment and then the second piece of the second segment. So let's go in and we can do these different pieces. So here we have Simpson's 1/3 rule. We had h h over 5 multiplied by the appropriate pieces. I can pull out f0 plus 4 times, f of x0, which was 0.2, plus 4 times f of x1, which was 1.296, plus f of x2, which was 1.74. So that first piece is 0.38. Then we can conduct Simpson's 3/8 rule on the remaining pieces. Once again, I'm going to use this, once again, I'm going to use x2 as the first point here. I then have 3 times my interior points, so that's x3 and x4, f of x3 and f of x4, and then my final f of x5 sits out all by itself. Notice that these segment lengths out front change a little bit. This is because that first segment is only looking at the piece, the first 2 segments, while the latter piece is using 3 segments. So we get a little bit, 1 extra value in here. Then to get the total integral, I just add up my 2 individual pieces. So I add up the integral from Simpson's 1/3 rule, and then the integral from Simpson's 3/8 rule together to get the entire value of my integral, which gives us 1.645. So I'm very close to the true value. We can continue to increase the order of my formulas, right? I could keep going to even higher order formulas that have smaller and smaller error, where every time I increase the order of the fitting polynomial between my points, I'm going to have a higher power of this. The error is going to decrease with a higher order of step size, and I use a higher derivative. So I'm going to end up getting a better estimate each time. I also want to comment on the truncation error and why we want to use what's called a closed form of the equation. So if we have an even number of segments and an odd number of points, this has the same amount of error as if I had 1 additional point. So in other words, if I have an odd number of points, 1, 2, 3, 4, 5, my error is equal to the error if I had 1 additional point in here. So in essence, I get better bang for my buck using an even number of segments and an odd number of points. So let's look at the higher order formulas. We can look at how many segments we're going to include, how many points are going to be included, and then what the appropriate formulas are out here. Here we have the truncation error associated with this, and you can see that we just keep adding additional terms to my equations as I'm moving outwards. So this is going to bring to a close the end of us talking about these formulas when I have evenly spaced segments. So I'm dividing my space up evenly. This is relatively easy to control if if I have some sort of complex function that I'm going to go in and then calculate the f at given points. This is not so controllable or usable when I have say, a piece of analytical equipment that's going to go in and make measurements for us. You can't always control how many segments that instrument is going to take. So we have to come up with a slightly different way to approach that problem. So this is going to be called our integration with unequal segments. In this case, I no longer get to pull out, H out front. Instead, I have to leave x1 minus x0, x2 minus x1, etc. out front. I don't get to pull this out. Therefore, we end up wanting to stick with our trapezoidal rule because this is going to be the easiest way to address these unequal segments. Let's do an example. Here I have a case where I have x's that are, say, measured with some sort of instrument, and I have different step sizes. You'll notice that this step size is 0.12, and the next step size is 0.1. The next step size is also 0.1, but then the next step size is 0.04. This may actually happen quite often when you're dealing with analytical pieces of equipment, which are going to take data as often as it can, but may not be taking that data at even points. So to solve for this equation with unequal segments, I can now employ, once again, my trapezoidal rule, but I'm going to do this piece by piece. I'm going to take this first segment and solve it first, then I'll look at the second segment, etc., until I get to the final segment. So I first calculate what my change in x is. So already written out there, it's 0.12. Then I can apply the height part of my formula. So that's 0.2 plus 1.309729 over 2. Right? So just pulling this right out of data. Then I can take the second piece. So in this case, my x2 minus x1 is 0.1, as pointed out over here, times the function value, so 1.309 plus 1.305 over 2. And I can do this again and again and again until I get to the final 2 points. The distance, or the xn minus xn minus 1 is 0.8 minus 0.7, which is 0.1. And then I can take the functional values, so 2.363 plus 0.232, divide those by 2, and sum all the pieces together. And here I get 1.948. So we can use these ideas of the trapezoidal formula for both equally spaced data and unequally spaced data. Because taking an integral using the trapezoidal formula is so common, MATLAB has a built-in function based on the trapezoidal rule. Straightforwardly enough, it's called trap-z. In this case, it will use the trapezoidal rule over those different values of a given y. If I give it only a single value, it's going to assume that that's our f of x's. And it's going to assume that we have a spacing in the x of 1. If I give it both an x and a y, it will then calculate the appropriate function. And it will return a single number z. You can also use the inbuilt function cumtrap in the same method. Here, instead of providing a single answer, so z is a single number, it will provide an array, where that array is the cumulative piece 1 to the next. So it'll return as z1, the trapezoidal piece from the first set. So x2 minus x1 times f of x2 plus f of x1 over 2, right? So it'll add up each additional piece. So then z2 would be z1 plus x3 minus x2 times f2 plus f3 over 2. And then carry this on and on and on. This is important if you want to look at how much of a reaction has completed as you go through time. The last topic that I really want to talk about is multiple integrals. We'll do this relatively briefly. We're going to use the same idea that we use for interpolating over multiple dimensions. But here we're going to do an integration. What we do is we pick a direction to work on first. So let's say I'm going to work first in the x direction. So here I would apply whatever formula that I want, say the Simpson's 1/3 rule, in the x direction. And I'll do that at each value of y. So in the first case, I'll take 8 minus 0, because that's the distance, times f1 plus 2 f of x2, which is 40, plus f of x3, which is 48, all over 4. And then I'm going to use that same rule for each value of y. So 1, 2, 3. So that first value ends up being 256. The second row, the second integral over that row is 296. And then the third integral is 484. So in essence, if I'm thinking about it like this way, where I have the integral of f of x, y, dx, dy, I first solve for the x integral, which then gives me f of maybe f prime y dy. So I've solved that out now. And now I can do, say, Simpson's 1/3 rule in the y direction. So here I take apart what my distance is in y. Right, so this is the distance in y. So this is dy. This was dx. And I use the values integrated over y to do Simpson's rule. So I get this 256, twice the middle piece, which is 496, and then that last piece, 444. And so I can then numerically solve out that last one to get the final value. Lastly, I want to cover symbolic integration in MATLAB. MATLAB is actually able to take in variables and recognize them as variables and perform integration. What we need to do, though, is to tell MATLAB that it's a variable. We do this using using symbolic integration. So what we're going to go do is we're going to use this sims function to tell MATLAB that x is a variable, as a symbolic variable, not a data holding variable. Then we can put in a function type and then tell MATLAB to integrate it for us. We can do this with either indefinite integrals by putting in the function comma x, or we can do this using definite integrals using int f comma x comma some range over which to integrate. Let's do this in MATLAB. So I'm going to switch over and we'll see you over there. So here we are in MATLAB. So the first thing that we need to do is tell MATLAB that we want to call a symbolic variable. So we can do this with this sims function call. So we just say sims, and then we can say x. You'll notice that MATLAB has changed the color of that character from black to sort of a magenta to let you know that it's a symbolic form. So if I hit enter, you'll see that it pops up in our workspace and it looks a little bit different. It looks like a cube with its name, and then we have this 1x1 sims. So we can tell that it's a symbolic form. Let's say I put in a function. So let's say 0.2 plus 25 times x minus 10 times x squared. Oops, I should have used plus. Now, when I enter this in here, my f of x is coming out in symbolic terms. You can tell because it's in the workspace name, we have this f, and it says sim, and we're seeing x's come out in this functional form. Now I can say, tell MATLAB to integrate f and by x. So if I hit enter, we now get the answer to my solution. In this case, it's right. I have this x cubed term, an x squared term, and a x term. And it's going to put this out in this, not in terms of decimals, but in terms of numbers, just because it's going to assume that that's what you wanted in. We could also do a definite integral instead of an indefinite integral by including a vector of points over which to operate. So let's say 0 to 0.8. If I hit enter this time, it will give me a numeric answer. Once again, in symbol terms as 484 divided by 75, rather than in a decimal format. This is very useful in MATLAB for solving complex integrals where you actually want or need to have an analytical form. With that, I want to review what we've talked about in class. We talked about Newton-Cotes integration, specifically as applied to our trapezoidal rule, our 1/3 rule, and our 3/8 rule. We then talked about how we can make a composite version of this by breaking up our the range of which we're integrating into smaller pieces in order to get a more refined answer. Then we also discussed that if I had unequally spaced data, I need to go back and more consider, say, the trapezoidal rule. And then we applied that. And lastly, we talked about using symbolic math in MATLAB in order to help get analytical forms of our integrals. All right, see you in class.